The first one will be given by Thomas VOLZ from the Center of Excellence for Engineered Quantum Systems from Sydney. So Thomas, go ahead.
Thank you very much for the introduction. And thank you very much to the organizers for giving me the opportunity to present the work that we're doing here at Macquarie University in Sydney. Since I don't know if everyone knows where Macquarie University is, I figured I'd just briefly introduce it. Oh, can I? Okay, here we go. So, well, you know the Sydney downtown, you know the Harbour Bridge, and you know the Opera House. If you take the train from here for about 20 minutes, northwest, you come to Macquarie campus, and our physics and astronomy department is located about here, and we've got about 30 academics working in quantum, photonics, and astronomy. And my group is actually shown here. This was pre-COVID, late last year in December at an Equus workshop down in Wollongong. So this is pretty much the team right now still. And Lorenzo here, who is also in the audience, is actually the one who is mainly doing polariton work at the moment. As you already mentioned, we're actually funded by Equus, which is a national center of excellence for engineered quantum systems. With the goal to engineer, well, we call it quantum machines. So we have three main programs: designer quantum materials, quantum enabled diagnostics and imaging, and quantum engines and instruments. And I just listed a fourth program, which is called the Translational Research Program. And I listed that for a purpose, because I'm going to come back to that in the end. But this program is there to support the other three programs and take scientific findings and help translate things closer to market. So really sort of trying to really identify applications and help translate that up the TRL ladder. So that's what this translational research program is about. And of course, most of you would know Andrew White, who is actually spearheading the effort, and the Equus, and is our center director up at University of Queensland. Now, the research that we do in the QMAP group is actually at the interface between quantum physics, nanotechnology, and material science. And it's not only that we do polariton research, we actually work with all sorts of different quantum emitters. So we work with color centers in diamond. We work with, obviously, excitons, exciton polaritons. We have recently started to look into 2D materials, and we're also working with rare earth ion doped nanocrystals. And what do we do with these? Well, we're interested in nanoscale sensing, mainly using our nanodiamonds. We have a very strong effort in optical trapping and levitation, which is partially supported also by Lockheed Martin to build novel acoustic sensors. And then a very strong effort is devoted, of course, to light matter interfaces and fiber cavities, and that's the very reason why I'm here today. The overall goal is really to engineer strongly correlated, from a scientific point of view, not a application point of view, but is really to engineer strongly correlated quantum many-body states of light and matter. But now to the actual content of my talk, or to the core of my talk. So you can see here the main system. So what I'll be talking about is our mechanically tunable fiber cavity system, where you see that there is a quantum well coupled to this mechanically tunable fiber cavity, and the light that comes in, the classical light that comes in, gets turned partially into quantum light, and that's what I'm going to talk about today. So the idea is to create, of course, single photon nonlinearities in this in the solid state, and to well, that you can then use to do, for example, quantum information processing. But also, I'm particularly interested in studying strongly interacting quantum fluids of light. The idea is really we take a nonlinear quantum medium, one of our emitter systems, pack it into a cavity, and form a light matter interface that turns classical light, so random light, into or Brownian distributed light into a highly ordered stream of photons on the other side. And of course, those of you who know my past a bit know that I've worked with such a highly nonlinear quantum system back in the days at ETH Zurich with Attach, where we studied strongly coupled quantum dots, and we looked at Jaynes-Cummings nonlinearities in this system. And of course, we all know that due to the confinement of the quantum dot, the nonlinearity is intrinsic. It's intrinsic in the quantum dot, and it's transferred to the strongly coupled system. And we end up having a highly nonlinear system that leads to photon blockade, where if you send a resonant photon onto the transition from the ground to the first excited state, a photon of the same color gets blocked and doesn't enter. So we have the effect of photon blockade. And of course, that the hallmark of photon blockade is really seeing anti-bunching in the light transmitted through the system. And here you can see a pulse correlation function with a strongly reduced number of coincidences at 0 time delay, which is indicative of strong anti-bunching in the system. Now, quantum dots, of course, have the drawback, and we know that they inhomogeneous in terms of frequency distribution, but also they have random positions on a sample. So we really, in the end, what we want is a highly ordered system. We want to maybe couple several cavities together and really study many body photonic systems. And so we need a different way of providing this nonlinear quantum medium. And one way, of course, is to use polaritons to dress our excitons and to engineer what we call a photonic dot. And so we use our strongly coupled excitons, our polaritons, which are half matter, half light, to engineer a nonlinear zero-dimensional system. So we take our 2D dispersion relation, and through actually photonic engineering of the wave function, through addressing this photonic part of our polariton wave function, we can then sort of start confining our polariton system and imprint discrete modes on our onto our polariton system, and we can then hope to make that confinement so strong that the exciton-exciton interaction becomes important on the energy scale of the system. And so we're going to concentrate on just one mode here. And of course, we're going to look at what happens to this mode when we start confining the system stronger and stronger. So this is the Verger et al. Paper from 2006, which predicts that when you make the confinement strong enough, then exciton-exciton interactions, or rather polariton-polariton interactions, will shift the two polariton state out of resonance and lead to the analogous effect of polariton blockade, analogous to the photon blockade effect, where if we probe the system now with resonant photons and we want to create one polariton in the system, a photon of the same color will not be able to create a second polariton due to the interaction shift. And of course, we have to compare the U with the line width of the polariton in order to be able to enter deep into the blockade regime. The U over gamma, which is our relevant parameter, needs to be large. And if we write U over gamma in a slightly different way, we see it scales directly with a Hopfield coefficient, the exciton-exciton interaction, and is inversely proportional to the area of the cavity mode, which is kind of what we expected. The more we squeeze, the stronger the polaritons will interact with each other. And using the theory from the Verger paper, essentially, we modeled our system, and for our typical system parameters, we were able to produce G2 of 0 as a function of laser detuning. Obviously, so here up here you see the resonant transmission of our polariton mode. 0 indicates right on resonance, and of course it's clear that when you tune your laser and you tune the tuning of, or you change the tuning of your laser, the effect, what you're going to see will change, because if you're slightly red detuned, the chances of reaching the two polariton state is further reduced, whereas if you're slightly blue detuned, you've got a finite chance of actually putting in two photons at the same time to reach the two polariton state. It just increases, and so you see a slight bunching on the blue side and a slight anti-bunching on the red side. All right, again, the system that we're using, you're probably familiar with it, but just as a recap, we use our mechanically tunable fiber cavities. We approach a dielectric mirror at the end of an optical fiber from the top. That forms a cavity, a stable cavity mode with the mirror that's integrated into the sample, and we've got our quantum well sandwiched in between. And as we tune our cavity length, we can tune the system in and out of resonance. And you see, as we approach the resonance, we see that we form polariton modes, lower polariton, upper polariton branch, and we get a nice avoided crossing. And it's this lower polariton branch that we are going to probe in our correlation measurements. And just as a recap, the fiber cavities are nice because they provide strong lateral confinement and a high Q factor, but at the same time, there is a fairly strong polarization splitting. So due to the birefringence mainly of the gallium arsenide, the modes are not, the eigenmodes are not sigma plus, sigma minus, but rather linear polarized modes, and there is a significant polarization splitting in the polariton modes. This is experimentally relevant. Now, what we find in our particular sample that we use for these experiments is that we actually, as we come close and as we probe the system, coming closer to resonance, as we look at the lower polariton resonance, we encounter strong losses as we come very close or around zero detuning. So you see the signal going down here in PL, so it's practically vanishing, but it goes beyond what we would expect from just looking at the Hopfield coefficient. And so instead of the lifetime going up, we see a strong decrease in lifetime, which we attribute to a trion resonance nearby. And it seems that our sample supports the trion resonance in the sense that we've got a fair bit of impurities. And if we pump the system at around 825 nanometers, so just below the band gap, then we see this trion resonance coming up in PL as well, which is a strong indication that this is the very reason why around here we see a strong loss due to that trion resonance. And actually, it's not only the loss or the lifetime that's reduced, but we also see it when we do a resonant transmission measurement. So these are just resonant transmission measurements as we change the cavity detuning. So we move across with the polariton resonance, we move across the trion resonance. We see the polarization splitting between the two modes. So this is resonant transmission. And as we move across, the overall signal drops drastically. Note the scale here. And at the same time, we see a strong background coming up. And I'll come back to that when I discuss my the correlation results. All right. Now, at the time of these experiments, we didn't have fast detectors available, so we resorted to the same method that we used back at ETH to probe our quantum dot cavity system back then. So what we use is we use fast excitation of the quantum emitter system, or the nonlinear quantum system, and thereby sort of eliminate the need to use fast detectors. We just have the time resolution on our excitation end of things. And so we shape our pulses to adapt to the lifetime of the polaritons, then send the pulses through our fiber system, our polariton system, and then probe the transmitted photons on a Henry-Brown and twist setup and obtain the pulse correlation function afterwards. And the results, so we were able to probe, so the sample that we were working with at the time had the problem of not giving many photons at the other end. So the transmission was fairly low. It was unnecessarily low due to the large number of layers. But we didn't know that at the time. So we had to integrate for quite a long time for each data point. So that's why we actually in the end probed the system at 3 different detunings corresponding to these 3 Hopfield coefficients. So you can see, so it's quite a busy plot. So I briefly run you through. So the top panel contains the transmission data. So we use a CW laser to scan across our polariton resonances. So we see the 2 modes, and we're particularly interested in the lower energy one, which is the dark blue one. But the other mode is present. We don't choose the polarization. Polarization is stable with which we probe, but it's not specifically adapted. And so we see the 2 modes, and we see also that turquoise background that grows as we come closer to the trion resonance. All right. So the middle panel I ignore for the moment, but the bottom panel is the corresponding G2 of 0 that we recorded in the experiment. So obviously the points are the data points, and the gray line is the corresponding theoretical expectation. And you see that the overall agreement is quite okay, except that there are a few points, for example, here. And you can't see my laser pointer. That is the problem. Okay, so here are a few data points that really lie above the one, and here is another one that's kind of really an outlier. But overall, the trend is okay. And when it turns out that the problem is really that we don't only have photons from the mode of interest that we're looking at, but we also have photons from the other polariton mode and from this background. And in order to quantify how much of the signal that we look at actually comes from the mode of interest, we introduced this T tilde function. So T tilde of 1 means all the photons that have gone through the system have interacted only with the blue mode here, with the dark blue mode. And you see that the most we can get is around 0.6, 0.7. So the maximum of T tilde indicates a region where we expect good agreement between our theory and the experiment. And that's generally true. And it's specifically also true, and I don't want to go into further detail, but it's specifically also true for the last graph where we see our best anti-bunching in the region where the T star is, or T tilde is also highest. And so you see here, these are the raw coincidence counts that we see there, and you see a clear dip. And also you see that clear dip in the integrated coincidence counts. And so from these data, we could actually extract a G2 of 0 of 0.93 plus minus 0.04 alongside the results that came from Attach's group at ETH Zurich. These two results really kind of for the first time really opened the door towards the quantum polariton regime, where really we created non-classical correlations from our polariton system. The two bunching peaks here are well understood. They're due to the crosstalk, and we wrote a little technical paper about that as well. All right, we were also able to extract polariton interaction constants, and essentially by taking correlation data and comparing it to our model, we were able to extract the nonlinearity for this particular detuning that we took the data at. And we were able to come up with this value. And this compares very well to what Attach also found in his system. Now, the point about our measurements and also Attach's measurements is that we don't rely on density, on determining the density of polaritons in our system. What we rely on clearly is knowing very well the waist size of our cavities, but we don't need to calibrate the intra-cavity polariton number very well in order to be able to extract the interaction constant. And this complements other experiments that were done in the polariton community, specifically with polariton BC experiments. Now, I want to acknowledge the people who have actually done the work. So Guillermo, who was the postdoc on the project and has moved on to Spain. Andrew, who was the student at the time, PhD student, and Matthias, who provided the theory simulations, and of course, Maxime, who worked closely with us on the problem, who's a regular visitor actually to Sydney and to our lab. And then, of course, samples and also finite element analysis were done by people in France, actually. Now, what are the next steps? So can you just give me the overall time? Because I think I started my presentation early and forgot to reset the time.
You still have 8 minutes. Okay,
cool. Okay. What is the next? What are the next steps? Well, so obviously, now that we have SSPDs, we would like to repeat the measurements in CW mode. We hope with the time resolution that we can get from our system, we'll be able to nicely resolve the dip in CW as well and explore the system a bit further. And we want to further do some photonic engineering. So we've started that experiment last year before COVID hit. Maxime actually fabricated some solid immersion lenses at NEL and brought them to Macquarie. We did experiments and we saw cavity modes with this in our fiber cavity, but the sample didn't quite work at the time very well. And so we couldn't continue the experiments, and we were waiting for a new sample when then COVID struck, and that whole thing got delayed, and we're going to resume these experiments again. I've got a student waiting in India to come to Australia. They're in lockdown currently, but once they can come, she'll work on unconventional polariton blockade. We've got a few ideas to see unconventional polariton blockade with a few cavity systems, and then we want to also study excitonic complexes and use Feshbach resonances potentially, but maybe more in TMDCs rather than gallium arsenide, but this remains to be seen. And of course, the future is then many-body quantum states. So I want to also just highlight the fact that we also did some experiments not only on resonant excitation of our polariton system, but also off-resonant excitation. So when you look at a quantum dot where you have a strong nonlinearity that really leads to a clear splitting and a real strong difference between the bi-exciton transition and the neutral exciton transition, then if you put a filter and just filter, for example, the neutral exciton transition, then you get anti-bunch light out, and thereby you can create nice quantum correlations. The question is, if you have a slightly chirped, interaction chirped system like the polariton system, slightly nonlinear, with U still much smaller than gamma, then can you do the same thing? What happens if you put a narrowband filter? Can you filter out the photons and can you get anti-bunch light that way? If you can, if you just pump the system off resonantly and just sort of filter the light out, what you could do is, of course, you could provide an electrically injected reservoir and then create quantum light that way by just simply putting a filter at the output. And indeed, what we found in our early experiments is that when you pump off resonantly and you do filter your light coming out of your system, you do actually get a G2 of 0 that is not 1, but that varies in a similar way to the resonant data. So for the red detuning side, for our low polariton resonance, which the lower polariton resonance is here, you see that on the red side, we find slight anti-bunching on the same order that we found for the resonant case, whereas on the blue side, we find again bunching. And it took us a while to work out what's going on in terms of theory. And again, we worked with Alexia Ofev and Maxime in Grenoble, but we came up with a theoretical model and we did some simulations. Again, Matthias did these simulations at the time. And we came up with an explanation and with results that are very much in line with what we find experimentally. Note the slightly different scale here. So you need to just look at the scale there of the x-axis here. At the moment, Lorenzo, the postdoc on the experiment, is actually doing some more theoretical work and is doing CW simulations to really sort of systematically study these off-resonant correlations that we found here. And from a scientific point of view, it might be interesting to see whether we can actually extract information from these correlations about the exciton bath from which we actually feed our polaritons. So that's kind of one of the motivations behind studying this system. But this is ongoing work, and we will still take a while to finish that up. Now, very recently, we've actually started a collaboration with Hamid Ohadi at University of St. Andrews. Hamid is working on cuprous oxides. He's going to put cuprous oxides into DBR cavities and wants to create polaritons that way. And of course, the interesting bit about cuprous oxides, inspired by the beautiful work that Manfred Bayer has been doing, cuprous oxides have strong interactions because, well, strong Rydberg interactions, and it would be great to use and make use of interactions for demonstrating something like Rydberg polariton blockade. And we have a joint PhD student who will spend his first 2 years at St. Andrews making samples, and he will then come to Macquarie for 2 years to carry out correlation measurements and demonstrate hopefully the nonlinearity of this system and work with that. As I said, we've also been moving in the 2D space a little bit, but we're just taking baby steps at this point. We on top of COVID, we also had the problem that, well, it's a nice problem to have, but we also moved labs very recently. So we expanded our labs and got new labs, but of course, that means we couldn't do measurements. So in the meantime, we've actually set up a small teaching lab setup for doing exfoliation. This was done by an undergrad student together under the supervision of Lorenzo. And the system actually allows both for transmission and fluorescence measurements in the future. And this is our very first flake. It's probably not a single layer, but we're getting there. So we're working on that. Now I come to the bit that I promised in the very beginning. So at the moment, we're using a spectrometer from Ocean Optics here to analyze the fluorescence coming out of our flakes. But in the future, we want to use our own product, and this is the story around the Equus TRL program that I mentioned. So actually, in fact, what happened here is that in our lab we want to do some measurements, and we couldn't do those measurements. We wanted to do nanodiamond thermometry, and we didn't have a good spectrometer for that. And we went to, and it happened that an astronomy colleague here had built an Eshel spectrometer for astrophotonics, which kind of sort of collected dust on his shelf in the lab. And he just mentioned that to me, and he said, "Oh, do you want it?" And I said, "Yeah, okay, let's have a go." And immediately we could do the experiments we wanted to do, and it really proved to be a very powerful technology for doing quantum experiments. And so we had several colleagues visiting, and they asked where one could actually buy such a device. And so we realized that there's commercial potential. I had a student finishing up his PhD, that's Matt here. And so he was willing to dive in, and we then applied together for a translational research grant from Equus, and we were able to develop a prototype spectrometer for actually ultimately commercial purposes. We went through a national accelerator program by the Australian Science Agency, and here we are. We founded a company, Redback Systems. I'm one of 6 co-founders. And we're about to deliver our first product at the end of the year, actually, in fact, to France. So we're quite excited. I just wanted to kind of give that as an example for what Equus does in terms of this translational research program that I mentioned in the beginning. All right, with this, I'd like to thank you for your attention. I'm always looking for talented PhDs and postdocs, even though at the moment it's tricky for them to come. But if you're interested, or if you know anyone who might be interested, please get in contact. And I also want to point out we have a new organization locally in New South Wales, which is called the Sydney Quantum Academy. I don't know if people have heard of it, but it's a sort of get together of all the universities in the Sydney basin that are doing quantum research, and it's kind of meant at training the future quantum workforce. And with this, I'm wrapping up now.
So thank you very much, Thomas. So we have 3 minutes for questions. So if anyone has any question, please raise your hand with the raising hand in the participant side. Yeah, Dima.
Well, yes, thank you very much for this very interesting talk. I have a practical question in order to, well, because I'm rather a theoretician, so I don't know, you were speaking about engineering and single photon sources. So as an engineer, what is the maximal value of G2 of 0 that you would seek for a device? I mean, is 0.95 enough, or you need 0.1 or 0.05, or what is the goal to really be able to set a single photon source?
I guess that was a sort of a very bold claim to have it a real single photon source, and you know, it's a long way off for to be competitive.
No, I understand. You were just showing non-classical anti-bunching, and it's well, yes, but it's not a single source photon source yet. But what is the goal? What is the value?
I don't have a number in my head. I mean, my goal is to study strongly correlated systems and not necessarily build ultimately that single photon source. But you could, of course, think about that down the track. So
I see. Okay. Well, thank you.
Is there any further question? Okay, so if there is no further question, we can just go ahead, so we can keep in time, so we can thank Thomas again for